used to send ECGs and they used to tell, sir, is there any abnormality in this like that? So I came to know that most of you people even doesn't know like basic ECG reading, and that's why we'll have this class today. And ECG classes are like something like your anatomy, nectar atlas, and your actual dissection. It is something like. So whatever the things I'm going to tell you or show you, so many things, or I may draw and make you explain, like understand the concepts. But actually, when you see the real ECGs, they are quite different only. So it is something like you'll be able to see so many good nerves, good muscles, and everything like in your nectar atlas. But when you go in the dissection hall or in the OT, and when you see everything is blood filled and something like a heap of nerves or like whatever it is, you will not be able to identify whatever it is or what finding you have there. Similarly, ECG is also something like that. So when you're understanding, when somebody is teaching you, you will be understanding it very nicely and everything, and you will be able to draw and show also. But when you are asked to show in the real ECGs, or when you are asked to read by yourself, it is quite difficult. And this is something like your PUC organic chemistry also. Until and unless you are in touch with ECG regularly, you will never remember it. So if, for example, today I have learned the class of ECG, and for next 6 months, if you don't touch the ECGs at all, if you doesn't revise, or if you doesn't come across ECGs, or you doesn't attempt to read them, sometimes like gap of 4 to 6 months, if you pass like this, you'll never be able to remember or like identify anything of the basic of ECG. So it is like whatever notes or whatever understanding you're making today, try to revise it at least once in 15 days or once in a month. Or at least if somebody sends you ECG or you see ECG, try to identify what are the abnormalities in it, okay? So as you know, this is a basic conduction system of the heart, and with this only we will start our ECG classes, okay? And as we know, this is the SA node here, and we have 3 conducting pathways for the SA node to AV node. Then we have AV node, then we have got, this is a common bundle branch. This is your right bundle branch, this is your left bundle branch, and then you have your Purkinje fibers at the tip. So actually Purkinje fibers are here also. So this is also Purkinje, this is also Purkinje, here also we have got Purkinje fibers. So the terminal fibers are your Purkinje fibers. It even goes up to here like this. So basically coming to our individual waves which are there. So as we describe our waves, like we have a P wave, then we have a small negative Q, then positive R, then a negative S, and then a T wave. So this is your P, then this is your Q, then this is your R, this is S, and this is T. So this is your atrial activity is detected by the P, that is SA node activity. QRS and T are mainly the ventricular activities are depicted by these 2 waves. Okay, so QRS mainly for the depolarization of the ventricle. T wave is mainly for the repolarization of the ventricle. So we will understand why these each waves are formed and what are the basis of each of these waves, like how they are formed, what is the basic. So to understand this basic of the ECGs, first you should be able to understand your basic like galvanometers physics or your PUC physics. For example, this is your galvanometer which is there, which is pointing at your 90. We have got a plus 90 degree like this, and we have got a minus 90 degree like this. So where does this arrow mark get deflected? So this is the pointer of your galvanometer. For example, this is the point A and this is the point B. We have got 2 points. If the current is flowing from A to B, okay, and you have connected a galvanometer here somewhere like this. So if the current is flowing like this, then the deflection will be towards this side. So if the current is flowing like this from B to A, it is flowing ulta, then the deflection will be like this. If the current is flowing, for example, this is the A point and this is the B point, okay. For example, current flows like this, the galvanometer comes plus 90. If the current the same flows in the opposite way, then it will become minus 90. Okay, it will like deflection will be opposite direction. If the current if the same 2 points are there here, A and B, and if the current is flowing either like this or it is like this perpendicular to both of the points, then the galvanometer will show no deflection at all. The same basic principle again holds good for this also. So what is the thing which you are having is this is the normal heart conduction system, right? For example, we have connected here A and B. Here 2 points are there. Okay, we will make this as one A point here. We'll make it as B point here. If this is the direction of the flow of the current from SA node towards the tip of the your LV. So if you are connecting a galvanometer here, if the current is flowing like this, so the galvanometer is going to have a deflection something like this. Okay, this is the way the galvanometer is going to deflect because current is flowing from SA node to like here tip of the LV. So something like that, or normal wave also we are going to describe now. So what is there is if you have like both of your atria are there, your SA node is there, this your AV node is there, then you have your both of the ventricle leg. Okay. So this is your ventricular physiology, which is like this, and actually heart is also slightly tangentially placed in the your pericardial sac. So what is there? The current is going from like this from SA node to AV node. From here it is coming like this, and then it is spreading like this all across the myocardium. So this is here actually happening. So what we'll do is we'll take this as a normal axis of the heart. So this is like slightly, it is heart is not straightly placed, it is slightly obliquely placed. So this is the turn which you are taking as a normal heart. So first what we'll do is we'll take a, if this is your normal axis of the heart, so first you are going to take a P wave as a SA node activity. So you are going to get a positive wave. Okay. Then what happens is then you are having a deflection which come from here to AV node. In AV node we have got a common bundle branch, and then we are going to have a split of the bundle branch like this. This is right and left bundle branch. Then we will have a Purkinje fibers which are going. So what we'll do is here you will take this as a interventricular septum now. Okay. This is the interventricular septum, and these are the ventricles which we have. These are the walls of the ventricle which is there. So this is the interventricular septum, and we have a small twig here from the left bundle branch which is supplying the upper part of the ventricle. Here we have got a small twig which is coming from the right bundle branch, which is also supplying the part of the interventricular septum. Okay, this is the actual anatomy which is there. So SA node, it is having pathway. Then we have got AV node. Then two bundle branches are there. We have got one here small branch from left bundle. This is left bundle branch LBB, and this is right bundle branch RBB. So we have got small branch which is supplying upper part of the septum. Then we have got here also lower part of the septum also. Okay. So what happens is the first wave which we have got is a P wave. Okay. Then as it is there, always left-sided bundle branch, when it impulse starts coming here, it is going to, this one is going to be depolarized first here. Okay. And then this twig is getting depolarized, and current is going to depolarize like this first. This is the, like you have to imagine, this is all the physics like how we used to imagine. So like this the depolarization is going to happen, but actually our axis of the heart we are taking it for lead to as like this. So both are going in opposite direction. The galvanometer is detecting like this, the current is going like this. Okay. So as we told that time, if point is like A to B, it is going, it will come positive. If it is like current is going like ulta, it will come negative. So something like our galvanometer is connected from this point to this point, but the current is almost going in the opposite direction, not exactly opposite, near opposite. So that's why what happens, the first P wave is going to be positive because of SA node. Then what happens, SA node to AV node, it is coming here. Okay, it is along the direction of your axis. So the P wave is positive. Then we get a small negative wave because it is going in the opposite direction here. This one, as it is going opposite direction, we are going to get a small negative wave, that is your first Q wave. Then what happens is the entire depolarization takes place like this. Because this is a small right ventricle is a thin one and LV is a thick one. Because this is going to overcome the, for example, this is giving your 5 negative potential. This is giving your plus 10 positive potential. Minus 5 and plus 10 is like, again, it will be something like plus 5. So it is going to have a big positive wave is going to get coming for you like this. And then lastly, what happens is, we'll take this area. This is the area where your pulmonary artery or like pulmonary conus arises like, okay. This is the area, right? So this area is going to be lastly depolarized. How it is going to depolarize is, this right bundle branch is going to supply like this ulta. It is going to come on the back side. This is the last area to be depolarized. So your current is going like this, and your electric current is coming in the ulta direction, and it is getting depolarization here. So the last part of this is depolarized in the opposite direction. So you are going to get it a small negative wave again here, because this last area, what I told you, here is the pulmonary conus which is coming here. Current which is coming like this, it is coming back and it is getting depolarized. We are getting a small negative area. And then lastly, repolarization is again, because depolarization is occurring like this, and repolarization also the same two directions but opposite event. So you are going to get it a positive wave here. So depolarization and repolarization are occurring at the same direction, but because they are opposite events, both you are getting as a positive wave. So this is the basic physiology which you people have learned or whatever. This we are not having much importance regarding your basic like understanding the different ECGs. Okay. But this is the basic waveforms which you should be able to identify and know. So what is the basic? Somebody is speaking. 1 plus Vamshi, somebody. Okay, I muted. Okay. So this is your P wave, which is because of your QRS complexes. Like, sorry, P wave is due to your sinus wave, like your SA node. Then you are getting a small negative wave because the initial part of the septum is depolarized in the opposite direction. Then we get a big positive wave because of the, so this is due to a septum depolarization. Okay. Then we are getting, next we are getting is due to main QRS complex. This main QRS wave is because of your ventricular depolarization. Then lastly, we have got a small negative wave. Again, you are going to get, this is due to pulmonary conus area, which is getting depolarized at the terminal event. So this is the lastly it is going to getting activated, and lastly this is due to repolarization. So these are the different waveforms which are getting due to your electrical rhythm. Okay, this is your SA node activation with P wave. So this much is your basic ECG waves you should be able to identify. This is only with respect to lead 2. Okay, this is not a general waveform for all the leads. Why it is like this, we'll discuss next. This is the basic lead form which we get because we assume the electrical axis like this. Okay, all these waveforms we have detected because we assume the main electrical axis is like this. Okay, if we think like something, for example, if we take electrical axis something like this, then we will get a different type of waveform only. Okay, so simply we'll just try it and see. As we told, it is going like this. SA node impulse is going like this, right? SA node is getting here and AV node is going here. Okay, but we are taking axis like this. Current is going like this. So you are not you are having the electrical current which is going at opposite direction perpendicularly. So either there should be no deflection or there should be biphasic deflection. Okay, as we said that time, if the point A and B are there, if the current is coming like this will show positive. If A and B are there, this will show negative. If the current is going in opposite direction like this or like this, either there will be no deflection at all or there will be a biphasic wave. So equally plus or minus. Okay, like this. If this is there, then P wave should become biphasic, first one. Then comes the QRS complex. Okay, in QRS complex, what happens? Initially, what happened here? Septal depolarization is going like this. Okay, this is again going in the opposite direction, so we may have a small negative wave. Okay, then you are having this wave. Again, these both are positive. See, this is coming like this, like our axis is going like this is going like this. Somewhere we may get a negative wave only, again bigger negative wave. Then lastly the repolarization occurs. Repolarization may be like this. Okay, so this is the lead axis which we may get if we take this as axis. So each waveform which will be you are getting, it will be different based on the axis which you are going to take. So whatever the axis which we have took last time was 60-degree axis, which was like this along the heart. Okay, this was the axis which we considered. So we got a normal wave like 1, this is 2, and this is 3. So 3 main waveform, P, then QRS, then your it's the atrial, and these are the ventricle, QRS and T. So this much which we got because of your axis as 60-degree which we took here. This is the normal axis which we are taking. So based on this, we will next move on. Okay, coming to your basic interpretations, whenever you get the ECG, first we will have some topics like what are the different points which we'll see here. First we'll see what is standardization. Okay, so standardization is something which is at the before each wave like this, something we will see in the ECGs. Okay, this is called as standardization. Okay, standardization here will take, see, this is the normal standardization. So here you have 1 centimeter is there. So this is 10 small boxes. This is called as standard. This is standard ECG standardization. Okay, this is the standard thing which we have. Okay, this is what is there, only 5 they have used here. This is half standardization. This is they have used double here. So this is 1 centimeter, 2 centimeter. Here it is 1 centimeter, here 1 centimeter. So total 2 centimeter they have used. This is called as double standardization. So why you should look for standardization initially is because, see, seeing this you will feel it as a normal ECG. If you see something this, there are something pathological condition, oh, ECG waves are very small here, so this is something small ECGs are there. So causes of your low voltage complexes are your pericardial effusions are there, pleural effusions are there, severe emphysema is there. So all these conditions are going to impede your cardiac impulse transmission for your electrical activity from your myocardium to your leads which are connected over the chest wall. So there is a impairment in the like transmission of the electrical activity. So that may cause your low voltage complexes. So low voltage complexes, you will think there is underlying pericardial effusion, pleural effusion, or your hypothermia, or your like something like your hypothyroidism can have low voltage complexes. or something like you have got high voltage complex which you think here. This is called high voltage complex, something like very big ECG leads are there, so small tall waves are there. So you'll think there may be hypertrophy, there may be enlargement, there may be something like ectopic, what you say, impulse might have been generated. So many false interpretations can happen. So that's why you should look each ECG. You should look for the square things which are present before the each ECG waves. That is, look for standardization. If it is 1 centimeter, then the ECG is standard. So then only you are going to consider like your abnormalities due to size of the ECGs. Okay, small wave, big wave, all those things you are going to take based on the standardization. Okay, and this is one thing you are going to see. Then you are going to see the ECG paper. There are different types of ECG paper used in the research fields and all, but we have what is called a standard ECG paper we have. So it is same thing like your graph paper it is. And we have got here this one big box, and in that we have got for small 5 boxes. Like in one small box is 1 millimeter and total it is 5 millimeter. And the duration is one big box is 0.2 seconds. So there will be 5 big boxes will form 1 second. 5 big box equal to 1 second. Okay, then like this is one big box, like this 1 2 3 4 5 big boxes will form 1 second, and each small box inside a big box, that is one small box, is 0.04 second. And this is the normal ECG paper which you have, and the speed with which it moves is 25 millimeter per second. This is the speed with which the ECG paper moves over the machine. Okay, this is the basic standards which we have kept. So first you should look for the standardization. I said this square boxes you should look, and then you should look for the ECG paper, how it is and what is the speed which has been set in the ECG paper. Now we will come to something like calculation of the rate of the ECG, like heartbeat, like what is the heart rate we are going to calculate. So we have many formulas for that. The simplest one is like 300 and 1500, two formulas we can use. So if we have to calculate the 2 RR intervals, for example, we have ECG like this, like this, like this, we are going. So we are going to calculate the number of big boxes between the 2 RR interval, like 2 R peaks or 2 positive or 2 negative peaks, either of that. And then you are going to see how many big boxes are there or how many small boxes are there in between them. If there are big boxes, then use the formula with the 300. If there are small boxes, use the formula with 1500. Okay, we will see with this. So to calculate easily, what we'll do is we'll take one wave which is exactly coinciding at some prominent line. Okay, so we'll take here. So for example, this one QRS complex is there. This is almost occupying at the one big line. Okay, from here, the next one is here it is. Okay, here. Now we'll calculate the number of big boxes here. This is one big box, 2, 3, 4. Okay, 4 big box and almost like small 2 big boxes are there. We will assume it to be exactly at 4 big boxes only. If we assume like that, then the heart rate would be 300 divided by 4. Okay, this is your heart rate for this patient, or this is the heart rate for your ECG. If you still want to calculate very accurately, then we will take it as small boxes. Okay, here see, this one is actually coinciding here 1, and here also it is almost at 1. So we have got 1 2 3 big boxes. It will be like 15. Okay, here 15 small boxes, here 1 2 3 4 5, around again 5 only we have. Okay, so there are 20. So what you can do is 1500 divided by 20 you can do. Okay, this is one way we can do. See, here also one more we have here. So we'll take one ECG where it is like almost coinciding with one of the big boxes or anywhere. See here, almost we have almost at one major line we have here. Okay, nearly at one major line we have here, and this is at the midpoint here. So almost it is like one big box. This is 2 big box. This is 3 big box, and half we have. Okay, so we can do 300 divided by 3.5 big boxes. So this is the heart rate for this patient. Okay, here we'll take this one only. Again, we'll calculate. See here, if we calculate like here, I think this is also not very accurate heart rate. Is there any other ECGs we have? We'll see. We'll calculate heart rate here. Here we have one more ECG. See here, this is again having here correctly coinciding at one of the main line here, and then we'll take here this one big box. This is second big box. This is third big box. Here 1 2 3 big box we have, and here we have almost half of that it is. So again it is 300 divided by 3.5. So this whatever number you get here, this is beats per minute. So if we take it as like 300 divided by 3, approximate will take it as 3 means we'll get 100. Okay, so we'll take it as 100 beats per minute. So the heart rate of this patient is 100 beats per minute. Because it is slightly more, we have to calculate like accordingly whatever we are going to get it. So this is the heart rate calculation. Next we'll come to about QT interval calculation. So we have got something called as QT interval, which are most important for arrhythmias detection. Okay, we have got something like long QT syndromes and congenital long QT syndromes. So many of your drugs which you have learned, like for example your ciprofloxacin or your amitriptyline, which you are using as antipsychotic medications, or your fluoxetine. So many drugs which we have now, we have prolongation of QT interval. So they are going to cause your arrhythmia. So what is QT interval like? What is the physiology? Which slope of the, like for example, this is your action potential of the cardiac muscles. So where it is going to affect, what is going to affect, it is too much into physiology. Somebody asked, sir, how S wave is negative? Like which S wave? I don't know. Which ECG you are telling? Somebody messaged me, sir, how S wave is negative? Which ECG, which S wave? Okay, so that is the QT interval. It is important, and that's why we have to calculate the QT interval. How are you going to calculate the QT interval? Is we have got a formula like QTC, that is which we use. C is corrected QT interval. So many times, whatever we are, so heart rate is seen in any lead. Somebody asked, yes, heart rate can be seen in any leads. Okay, there is no specific things like you have to see from that lead only, this lead only. You can see from any leads. We'll finish this QT interval and we'll come to the heart rate questions. Okay. So QT interval, whatever you are seeing here, no, in this ECG, for example, so many QT intervals which are there. Whatever you are seeing here, that is actually not the QT interval. So what we'll do is QT interval you will calculate by corrected QT interval is calculate the QT interval divided by root of RR interval. So this is the formula which you are going to use it for calculation of corrected QT interval. So what you will do is you will calculate the Q wave to T wave here. For example, this is the Q wave, then you have to take the T wave. This one you have to calculate the QT interval, whatever it is. Then you are going to fill it here. So for example, we get 30 something. Then we will take the RR interval here. Okay, we will take like for example something it is 50. Okay, then we will do it as root of 50. So whatever we are going to get this value, that is called as corrected QT interval, QTC. That you have to say. For example, it should be like 0.44 seconds. Okay, so 0.44 milliseconds is the normal value which we have. It is slightly different for males and females, like 0.44 to 0.46. Okay, some book you want to give it as 0.48. Okay, this is the normal. If there is a prolongation of QT interval, then there is a more risk for arrhythmia. That are the important things which you are going to calculate in case of QT interval. And the crude waves, the crude way how we are going to calculate it is, most of the time what we'll see is if this is nearly half of this one, okay, then QT interval is not prolonged. Visually we'll see it, okay, approximately QT interval, what is the length we are going to see, and just we'll compare it with the RR interval. If it is within the half of that, then most of the time it looks like there is no QT interval prolongation. If this appears to be more bigger than the half of this length, right, this R to this R, if it is more bigger than this QT interval appears to be bigger than this RR interval, then there is something we are going to find it like any abnormality is there. Some questions some people have asked. One is, sir, heart rate is seen in any leads. Okay, that is like any leads you can calculate, and we will finish that. One more question here. See, heart rate, what happens is if there is a atrial fibrillation, okay, atrial fibrillation, there will be irregular heart rate will be there. Okay, at that time, what we will take is we will take a 6 seconds length of ECG you are going to take it. Okay, 6 seconds of ECG you are going to take. For example, 1 second, that time how many big box we told? 5 big boxes will be one. Okay, so 6 seconds it will be like 30 big boxes. Okay, we are going to take a continuous strip of 30 big ECG. 30 big box should be covered in ECG. There are so many like RR intervals will be like this. So for this example, it is atrial fibrillation. No, see here there is so many. For example, this is big RR interval. Here we have a small. Here we have very small. So there is a variation. You cannot give a definitive like what is the heart rate. So what we'll do is 6 seconds we are going to calculate. Okay, in this we are going to calculate how many RR are there here. 1, 2, 3, 4, 5, 6, 7, 8 are there. So we have got 8 QRS complexes are there in 6 seconds. So how many will be there in 60 seconds? So this is another way of calculating your atrial fibrillation. In case of atrial fibrillation, how are you going to calculate heart rate is by this method. And so calculate in the millimeter or time, somebody asked, you can aram se calculate in time only, because we are going to get the like for example you are getting like milliseconds, right? So we are going to get it in seconds only here, so you can calculate the root of RR interval in time also, there is no issues regarding that. And most of the time what happens is only this QT interval corrections will be in reality only will go for real calculations most of the time when we have doubts of there is a QT interval prolongation, if the patient is all risk of arrhythmias, or if the patient is receiving any drugs, okay, any drugs which are going to cause QT prolongations, or the patient has received antiarrhythmic drugs. You know that so many antiarrhythmic drugs are per se arrhythmic, okay. For example, your class 1 interval antiarrhythmic like procainamide and your quinine, quinidine, they are itself arrhythmogenic drugs. So at that time, you are going to use this QT intervals prolongations, okay. But in practice, we will not usually use. You can calculate in time. So QT interval is not a like what you are going to do is like you can put RR in time and you can finish it. And one more, somebody asked one more question here, that S wave, how it is negative, somebody did not answer only. Okay, we'll go next. Okay, so now nomenclature of QRS interval, like QR intervals. So see, this is the new thing which I don't know how many people have read or not read. So many things are there, like we have got different nomenclatures which we use for QRS complexes. Here what is going to happen is, see, for example, this was the normal like waveform which we see, this will cause Q, R and S, okay. These are the arbitrary different type of naming we give here. For example, see, this Q wave is very small here. So we are going to use small letter Q. Compared to this, we have a little big Q here. We will use it as big Q. See, this is also big here. This is Q. I think if you compare these both, I can again write this as Q and this as Q. Okay. So there is nothing like definitely this much mm only. This is the size and all. Arbitrarily, it is given like small one is given as Q and bigger one is given R. See, and one more thing here, we don't have a positive R wave in between. It is not there. So directly we have got a Q wave here, and then it was a S wave which will come here. Right? See here. This R wave is missing for this ECG lead. This R wave is missing. This Q and S only are two positive negative waves are there. So they have combined this and made it as QS complex. The Q will call it as QS complex. Okay. And sometimes what happens is, see, this is type of ECG which we get here. See, normally what we should get two negative and one positive. What happens here is one positive, one negative, and one more positive. So what we did is R, S, and R dash. See, here Q wave is not there only. So they have not mentioned it as Q. Q is not there, not even small, not even big. Then R is there, S is there, then R dash is there. Something like, for example, the same ECG, if it has become like this, no, almost if both were of equal size, then you can make it as RS R dash also. For example, if this is bigger and this is small, then you can make it as RS R dash, chota r, something like that. So whatever you want, you can make it. It's just arbitrary notification. See, that one you should remember. Okay, this is QRS here. Whatever I have written here, QSR. See here, this Q they have written. I think if this was slightly bigger, no, I think they would have made it kiss Q. Okay, or something like this. It will be Q R, then this will be small s, or something like this, like this. Okay, then this will be Q, this will be small r, then this will be s. So many different type of notations which you can make for QRS complexes. Not very important as such, but you should be knowing. We'll discuss about these in bundle branch blocks. Okay. Now coming to something called as J point ST segments and T waves. So this is the point which we call it as J point in ECG. So J point is where your negative wave of like ECG comes into end and then your ST segment starts. See, this is the point where we call it as J point. So J point is a point which you consider for ST segment elevation or non-ST segment elevation or depression, whatever things we are defining. But J point can be elevated in case of non-myocardial infarction also. Non-myocardial infarction, there are many conditions. That time also J point can be elevated. But J point, that you should remember, it is one of the important locations in your ECG wave which you consider for ST elevation and ST depression. We'll come to it in the later part when we deal about MI, myocardial infarction. We'll come to the J point again. Okay. So this is a J point is depressed here from the baseline. This here J point is slightly elevated from the baseline. So that much we are going to remember at this point of time, and we'll move ahead again. Okay. See here, this is the ST segment elevation. See, this is the baseline. This is the J point which we have here. Okay, this is the J point which is almost at the normal baseline. See here the J point is elevated. So this is the J point which is elevated here. So this is your STEMI. So your ST elevation myocardial infarction. Okay, here the J point is depressed. See, this was the baseline of ECG, and this is the baseline of ECG which is going like this. You have got a J point which is depressed here. So this is your N STEMI. This was the baseline of your ECG here. So we have got elevated J point. This is the baseline of ECG which is at the normal, and J point is also there only. Okay, somebody put one more message. Sir, which will be baseline? So baseline usually will be taking the PR interval is there, no? This will be taking as baseline. Okay, for example, we'll go to the old ECGs, anything like this one ECG will see. See, this is there, no? Here, this ECG I'm not here. This line is there here, right? PR interval line. 1 second, I'll show you. See, this line is there, no? This line is there, that is we are going to take it as PR interval. Okay, P wave and QRS complex small line is there, no? That line, and post T wave to your next QRS complex. That is we are going to take it as a baseline. Why it is not marking, I don't know. This line, this is the baseline. So this small QRS complex here and this one, this much you are going to take baseline. This is the elevation which we get here most of the time. So this is the region which we get a abnormality here. So these are the areas where J point elevation comes. So this is your baseline. Here also, this is the area where we get abnormalities. So these are the baselines. This much is I think basics of waveforms. I think this much is more than enough. And so what is the purpose of standardization, somebody asked. Purpose of standardization is, see, for example, in case of your pericardial effusion or your myocardial any other diseases or your severe emphysema, what happens is so many small changes will be there. For example, if you see, we will take as 0.1 millivolt, okay, or your small 1 mm box which is there, which is the signifies your MI. Okay, definition of MI goes with so many times elevation of ST segment of 0.1 mm also. 0.1 mm is one small chota box in this elevation also goes for your myocardial infarction. What happens is sometimes if you have emphysema or associated pericardial effusion or something diseases are there, at that time what happens is your elevations will not be 0.1 mm because the ECG has come very small, chota one you have got, 0.1 mm not be there, it will be like 0.05 mm elevations will be there. So at that time, if you have doubt, no, you have to increase the standardization. You make the standardization to 2 centimeter, like your 20 mm you make it. Okay, then you get the ECG. See if the elevation is increasing or what. Okay, then you compare. If you make, if it was normal standardization and what is there, if it was like increased standardization, what is there? Are you able to identify any other abnormalities which you have missed with normal standardization? That's the purpose of changing of standardizations. Okay, any doubt here? Okay. Coming to lead placement, we will not go much in detail regarding the physiological aspect here. So many things you have learned, like in the Einthoven triangle are there, plus, minus, minus, plus, 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 minus, minus, so many things are there. Okay, if a person is there like this, he has 2 hands and you put a head here. Okay, so many things are there which you have done, and all those things are there which will not go in detail much regarding this one. Okay, why that is plus there only, why it is minus here only. We don't, as physicians, we don't need much here. So we'll just go to the main part. Okay, main part is like here we will come to this one image. Okay, see, this is the lead system which we have, which you commonly know it as 12 lead system in the ECGs. Okay, so we have got here 1 2 3 4 5 6 in the person who is standing there with a wheel, like, okay, in front of him. We have got AVR, AVL, and you have got AVF, and you have got 1 2 3. So 3 plus 3, 6 leads we have got here. So this 1, this is 2, this is 3, this is 4, this is 5, and this is 6. These are 6 leads here we have, and here we have got V1 to V6. These are 6 leads here. So this one we call it as chest leads. This one we call it as limb leads. Okay, so totally chest and limb leads, totally we have got a 12 lead ECG. So this is the 12 lead ECG which we have in our daily practice. So we'll come to each lead now. I think I'll give one more link. It is 1 minute only remaining. I'll cancel and I'll get you one more link. Okay.